Hello, I would like to start by thanking the organizers for inviting me to give this talk. Under normal circumstances, I would have encouraged you to ask questions throughout the presentation. Unfortunately, this is not possible. However, if you do have questions, feel free to ping me after you see the talk. Let's start by introducing the continual learning problem. This is typically done through the setup that you need to evaluate an algorithm on continual learning and through the list of desiderata that we expect from a continual learning solution. The setup is that you have k tasks that you need to learn sequentially, where you have access to only one task at a time. And there is an explicit assumption that at some point in the future, you'll get to revisit tasks that you've seen initially. So for this reason, it is important to maintain performance on all the tasks that you've learned so far. Crucially, the agent or the model has no control over when you switch a task and to which task you switch to. And the list of desiderata usually starts by asking that the solution on a continual learning problem should be able to mitigate catastrophic forgetting. So that means that after you've reached a certain performance when learning task 1, you should maintain this performance and get the same level of performance after you learn task 2, 3, 4, and so forth. There is an expectation that the model should have a fixed side, both in terms of computation and in terms of memory usage, or at least if this is not possible, for this growth to be sublinear. Crucially, in continual learning, it's quite important for the algorithm to show forward transfer. That is, the solution needs to be able to leverage all the knowledge that it has acquired so far in order to learn faster and better a new task that comes along. Furthermore, if the new task is related to previous tasks that the model has learned, it is expected that by learning the new task, you should improve performance on those previous tasks as well. However, if we limit the definition of continual learning to these two aspects, the setup and the list of desiderata, continual learning becomes ill-defined. And I myself have been using such definitions in the past quite often. Just to highlight this property, let's start with the list of desiderata. The way people have approached it in the past was to figure out algorithms that would resolve a small subset of these. So for example, an algorithm might be focusing just on catastrophic forgetting and provide a potential solution to mitigate catastrophic forgetting, or the algorithm might be fixating on forward transfer and come up with a particular approach that maximizes forward transfer. And the hope has been always that at some point in the future, someone will be able to pick all of these different approaches and somehow combine them in one algorithm that is able to exhibit all the properties that we require from a continual learning solution. However, it's becoming apparent that this is not really possible. And many of these properties are actually in contrast to each other. So you cannot ask a system to remember everything and at the same time to have a fixed capacity or to be able to do forward transfer. So what a continual learning solution needs to do is needs to find the right trade-offs between all of these properties. And the problem with this is that the definition that we have so far does not give you any clue of what are the optimal trade-offs that you need to discover. So in this sense, continual learning becomes ill-defined, and it becomes extremely hard to come up with a way to compare different algorithms without having a particular domain or a particular setting that we actually care about. Another issue with a definition of continual learning that strongly relies only on the setup itself and the list of desiderata is that it leaves the door open for several questions that become really hard to answer. So one such question is, why do we study continual learning at all? Is continual learning a reinforcement learning specific problem? Because in reinforcement learning, the sequentiality of the tasks is natural, while in supervised learning is not. Why are simple solutions that involve just storing the data of all the tasks that you've learned so far and using this stored data to construct the multitask solution, why are those solutions not enough? Why are we looking for alternatives? Is catastrophic forgetting really important? Should we even include it in the list of desiderata? And there's also the question whether the implicit assumptions hidden in the protocol that we use, if they are natural or not. For example, the setup itself assumes that there exists a multitask solution of the sequence of tasks that we that we observe. Otherwise, otherwise enforcing the system not to have catastrophic forgetting makes no sense, and is unclear whether in natural tasks that we would want to apply this algorithm later on, if this property holds or not. In what follows, I would like to offer a different framing of continual learning in the hope that by looking at continual learning from an optimization perspective, we can at least partially answer some of these questions. At this point, I want just to make it clear that by no means my goal is to say that this is the right way to frame continual learning, or that by looking at continual learning from an optimization perspective, you're able to answer all of the questions before. But the hope is that this will provide new insights, potentially new approaches, and will help in motivating why continual learning is a crucial problem that we need to address now in machine learning. Let's start by talking a little bit about optimization for neural nets. So the workhorse for deep learning is stochastic gradient descent, which is this iterative process where at every point in the process, what we do is we try to estimate the steepest descent direction, and we take a small step in that direction. And we repeat this many, many times until this gradient that we use to define the direction in which define the direction in which we need to move vanishes. And at that point, we've converged to a minima, which is a solution that we're looking for. So if we think about the gradient and what it does, one way to interpret it is that the gradient of the loss to a particular parameter for a particular example tells us what would happen if we increase or decrease that parameter. So it tells us if we need to increase the parameter in order to minimize the loss, or we need to decrease it. And this is done independently of all the other parameters and independently of all the different data points. And the way stochastic gradient descent works is that you take all of these observations for all the data points that you have in your mini batch and for all of your parameters separately, and you average them. At least you average them over the data in order to find out what is the best change of that particular parameter in order to improve the loss on average over all the examples. And you can see this as some form of tug-of-war dynamics, where each example is trying to push a weight towards itself. And there is this tension that is created between the examples that leads for the parameter to settle to some optimal value, which minimizes the loss globally. From this perspective, we can think that the way credit assignment is done when you're optimizing with stochastic gradient descent is through this tug-of-war dynamics. And by credit assignment, I mean how the network decides which parameters should be used to model which part of the function, which features, and which part of the data. And for this tug-of-war dynamics to work, there is an important requirement that data is sample IID, or that all the data is available at the same time when you're computing the steepest descent direction. Because the only way this works is if all the examples are pushing the parameter towards themselves. If some particular class of examples is completely missing when you're computing the update, then it's the same as playing this game without an opponent. And then trivially, the data that exists when you compute the update pushes the weight all the way to themselves, leaving the model to be able to model only this particular subset of the data. And crucially, this tug-of-war dynamics also highlights the fact that there is no explicit knowledge composition in stochastic gradient descent. The way knowledge is acquired is through this tug-of-war between different parameters on different data points, and it happens in parallel, and it's not an explicit composition where some features are reused in a very particular way by later on. And the point that I was trying to make is that we can look at catastrophic forgetting and understand catastrophic forgetting as a failure of learning to do proper credit assignment. So in particular, catastrophic forgetting is exactly the scenario when you have this tug of war on a particular on all the parameters of the model, and one of the opponents in the tug of war game is missing, which is the task that is not the tasks that are not available at that point in time. And that what that does is forces HGD to pull the parameters all the way to the solution of the active task, forgetting all the other tasks that you've seen so far. So if you believe this, and if you take this view into account, then continual learning becomes the study of credit assignment in learning, and in particular the study of the effects of this tug of war dynamics of stochastic gradient descent. Resolving continual learning means or has to imply finding a better or at least a different mechanism for doing credit assignment, and continual learning is crucially a property of the optimization algorithm that we use, and it would apply equally to all sets of settings, from supervised to reinforcement learning or unsupervised learning. So we can already see that this particular framing of the continual learning problem provides some of the answers to the questions that we've enumerated previously. So for example, it explicitly says that continual learning is not specific to RL, it's specific to any algorithm that is relying on stochastic gradient descent or that exhibits tug-of-war dynamics through their learning. It also highlights why simply storing the data is not necessarily the solution we want, because by storing the data and emulating the multitask solution, we're avoiding to answer the fundamental question that continual learning is about, which is how can we do credit assignment within a neural net differently. So armed with these ideas, I wanted in the second part of my talk to quickly go through two recent works that I've been involved in. They're all work in progress, and all of them look at continual learning from an optimization perspective. And the goal of presenting these two works is to show how taking this framing of continual learning into account can provide new solutions or new ways to think about continual learning. So the first work that I want to present, it's about understanding the role of the training regions for continual learning, and this is joint work with colleagues from DeepMind and Washington University. So this work starts from looking at forgetting of task one after you've learned task two. And in particular, what we do is we look at the difference of the loss on task one at the solution of task two and task one, and we take a second order Taylor expansion around the solution of task one. So we do this, so one might argue that doing so is a very crude approximation, but there is sufficient evidence in the literature that analyzing the loss surfaces of neural nets that show that these loss surfaces are better behaved than we expected. And also, as a side note, this particular assumption has been made previously for many of the state-of-the-art continual learning approaches, including things like elastic weight consolidation or any approach that relies on a Gaussian assumption to model the posterior of learning a solution. So if we take this approximation, I can see that the forgetting can be approximated by the displacement, where the displacement of the parameters delta W, where delta W is the difference between W1 star and W2 star, multiplied with the Hessian of the loss at the solution for task one. So the Hessian of task one at the solution of task one. And we can furthermore, we can furthermore upper bound these approximations by the largest eigenvalue multiplied with the norm of the displacement. What this tells us is that if, when we learn task one, we converge to a wide minima, one that has very low curvature in all directions, then this would implicitly reduce the amount of forgetting that we will see when we learn task two. And furthermore, it is important to learn task two in such a way that this displacement vector is also minimized. Next, I wanted to highlight that there is a growing body of works that are studying the width or the local geometric properties of the minimals that we've learned. And this is usually done because of this hypothesis put forward by Hochreiter and Jürgen Schmidhuber that says that the reason why we generalize so well when we train neural nets is because they tend to converge to flat minima. And this follows from the fact that the flat minima tends to be more stable, and the hypothesis says that the inherent noise in the stochastic gradient descent process forces the neural net to escape the Bayesian of attractions of sharp minimas. And given this hypothesis of how generalization works for neural nets, there is several works that are looking at how you can hyper-optimize your training regime in such a way that you converge to as wide as possible local minima. And our approach for this paper was to borrow all of these techniques that were used to improve generalization and to test to see what effect they have in terms of forgetting in a continual learning setting. To do so, we've created two modes of training, one that we call plastic and one that we call stable. The plastic training regime is a typical training regime that has been used in the literature quite often to construct the baseline. So this is just a stochastic gradient descent applied to the neural net, while the stable regime employs a bunch of techniques that have been proved in the past to increase the width of the minima. So in particular, these techniques include dropout that has been previously studied as a solution to continual learning as well. But besides dropout, also a particular learning rate schedule that starts with a large learning rate that is being decreased over time, and decreasing of the batch size as we move from one task to another in order to augment or to increase the amount of noise in our updates to force the model to keep converging to wider minimas. If we run for two typical continual learning problems, if we write these two settings, so we run it in the first two columns for permuted MNIST and in the second two columns for rotated MNIST, we noticed that these techniques indeed lead to wider minimas. So we can see here the plot of the spectrum of the eigenvalues of the solution on each task, and we can see that this spectrum is much lower when you train in a stable regime versus when you train in a plastic regime. Also, it seems that the displacement, so the delta W norm is also decreased in the stable regime. This doesn't come directly from the approximation we've presented, but there could be two potential reasons for it. One is wide minima in general need small weights. So by asking the model to converge to wide minima, we're asking to find minimas close to zero, which implicitly means that these minima are closer to each other. And the second reason is every time we learn a task, we don't actually run until convergence, usually stop in the vicinity of the minima that we're converging to. And as this minima becomes wider and wider, this area, this vicinity becomes, the volume of this vicinity becomes also larger. So you can actually stop much further from the solution of the task that you're learning and closer to the solution of the previous task that you've seen. And we can see that in this stable regime, it also follows that the amount of forgetting is minimized. So we can see here the performance on task one, and it doesn't decrease as you learn multiple tasks, while in the plastic regime, the amount of forgetting is considerable. We wanted to finally test this plastic versus stable SGD on typical problems, comparing with a bunch of typical continual learning algorithms from the literature. And the main take-home message from this table and from these experiments that we've run is that at least on these typical benchmarks that people have been used in the literature, so namely permuted MNIST, rotated MNIST, or split CFAR, by just employing these techniques that try to look for wider minima. So these techniques like looking at the learning rate, looking at batch size, you get competitive results. So this is quite important because these techniques are readily accessible. They're much easier to use, and usually they're just part of the pipeline. It's just a matter of hyper-tuning them with a focus on trying to converge to this wide minima. Another side message of this experiment, it might be that the settings, the benchmarks that we've been using so far might not be up to par. There might be somewhat too easy, and For them, we don't yet need to have complicated continual learning algorithms in order to reach decent performance in terms of catastrophic forgetting. As a next step for this work, our aim is to check the effects of combining these techniques, of combining this particular style of hypertuning the training regime with known continual learning algorithms to see if by combining these together, we can get even better behavior than those reported in the literature, or if these two things put together would not give you more than just normal HGD with a stable learning. Moving forward, the second work that I wanted to talk about is focusing on forward transfer. And I believe that forward transfer is a very interesting concept where traditionally people have been thinking of forward transfer from the perspective of being able to learn much faster a new task. So in this work, we actually ask a slightly different question, which is, does the model itself preserve its plasticity? And what we mean by this is a model, after it's been pre-trained on multiple tasks, able to reach the same level of performance as if it would have learned the task from scratch if we don't constrain the number of updates that the model is able to learn. And this work is joined with colleagues from DeepMind and also from Imperial College London. The work starts from an observation put forward by Esch et al. In a paper that discusses the difficulty of warm starting neural network training. And in this work, what the authors have done is they take a known data set, in this particular case CFAR, and they randomly subsample half of it. And they train a ResNet on half of the data set and check how this ResNet that has been pre-trained, how well it generalizes when you fine-tune it on the full data set compared to a model that is trained directly on the full data set. And what they observe is that there is a generalization gap where the pre-trained model performs worse, regardless of how much of the budget of updates that you allow, performs worse than a model that has been trained from scratch. And in this work, we want to analyze this particular observation and try to understand its implications for continual learning. And to do so, the first question that we wanted to look at is, how much pre-training do you need to do in order for this generalization gap to appear? And as you can see from this graph, and as it is in some sense expected, the more pre-training stages that you do, the more do you learn this first task, the bigger the gap would become when you start to learn the second task, when you try to fine-tune the model on the full data set. However, it is sufficient to do just very few epochs on the first task in order to have this gap appear. And just as a note, the number of epochs that you need to do is way smaller than the number of epochs that you need to converge on the pre-training task. So there is no way that just simply doing early stopping on the first task would help you to completely eliminate this generalization gap that we're observing. To move closer to the continual learning setting, then we ask the question of what happens if you have multiple pre-training stages. And interestingly enough, we notice that the more pre-training stages, so the more tasks you learn before you fine-tune on the final task, the bigger the gap becomes on the bigger task. And this observation is quite important for continual learning or for lifelong learning, where the expectation is for a model to go through many, many tasks one after the other. So if every task that we see makes us less able to learn the final tasks, this becomes problematic. Furthermore, in order to get closer a little bit to continual learning setting, on the graph on the right, we have explored what happens if the way we sample these pre-training subsets is not IID, but we bias the sampling process towards different classes in the data. And we do this in order, again, to get closer to a typical continual learning setting and to make the data distribution between tasks to be more and more different. And we noticed that, at least in sort of given the protocol that we've used, the more the distributions become different, the larger the gap would be, which again, it's quite important for a CL setting where these tasks tend to be quite different one from each other. The other question that we wanted to look at is whether this gap is a side effect from this abrupt switches between tasks. So in particular, what we wanted to do is we wanted to blend and to smooth out this transition from the pre-training data set to the fine-tuning data set. And what we noticed is that even when this transition becomes very smooth, the gap is still present. So it seems that this generalization gap exists no matter how learning happens. And this is actually quite an important observation for reinforcement learning, where the model is always smoothly transitioning from one data distribution to another, because the policy keeps improving, so the distribution of the data that we're observing keeps changing as well. Finally, we wanted to start providing some tools of approaching this problem, of approaching the question of how can we understand why this is happening, and hopefully how maybe we can address this problem, or what we need to do in order for this generalization gap to disappear. And one first hypothesis that we wanted to analyze was whether this generalization gap is a side effect of the stochasticity of the updates of gradient descent, or if it's a property of the loss surface itself, if this would appear if you'd follow the gradient flow as well. And one way to think about this is if we go back to the original hypothesis that we mentioned in the previous work about the flat and narrow minima. One hypothesis would be that the pre-training stage somehow reduces the amount of noise in the updates to the point that when you go to the fine-tuning stage, you're not able to escape the sharp minimas anymore. And what happens is a pre-trained and fine-tuned model would more likely converge to a sharp minima, while a model that has been freshly initialized would converge to a flatter minima. And our first step towards understanding this hypothesis was to try to look at what would happen if we scale up the learning rate when we move to fine-tuning, and what would be the optimal learning rate in the fine-tuning stage in order to make this gap as small as possible. Know that in the previous settings, while we did hypertune the learning rate carefully, we did this over the entire process. So as in a typical continual learning setting, we assumed that the learning rate would be constant throughout this process of pre-training and fine-tuning. And what we find is that if the learning rate is increased by an order of magnitude, then the gap becomes smaller. So just to be clear, this is an increase of learning rate compared to the pre-training learning rate, but it's an increase of the learning rate also compared to the optimal learning rate when we learn from scratch. So this highlights that compared to learning from scratch, when we fine-tune, we need a much larger learning rate in order to scale up the noise and hopefully escape narrow minima. While this experiment on its own does not validate the hypothesis, and there are potentially other reasons for this phenomena to happen, we regard this as a first step in our experimentation, and we're currently looking at different ways to look at this hypothesis and trying to find a way to estimate the amount of noise in the updates and trying to artificially augment this noise and see if by any of these techniques we can approach a solution to this generalization gap. Just to conclude my talk, what I've tried to do today was to introduce a different perspective on continual learning, which is that continual learning is the study of how to do credit assignment in learning. It's catastrophic forgetting is a side effect of this tug-of-war dynamics of HGD, in the hope that by looking at continual learning from this perspective, it offers some motivations of why continual learning is an important problem to study, and why, to what extent some solutions are what we're looking for when we're looking for solving this problem, and also maybe provide hints in different ways of approaching the continual learning problem, and potentially different solutions. Thank you. And as I mentioned before, if you have any questions, feel free to write me an email.